All right, welcome back to another LeetCode video. We're currently progressing through the list of graph problems here on LeetCode.io. It has this nice curated list of all LeetCode 150, the blind 75, and I think also the LeetCode 250 problems, which is a collection of prototypical LeetCode problems that you can get asked in interviews, categorized by the data structures or the techniques used to solve them, like sliding window binary search. And we're looking at the graph problems. We just completed number of islands. And next we're going to attempt the maxed island area problem. Max area of island problem. And I have solved this before, yeah, over 2 years ago. So let's see if we can solve this right away. I should be able to. All right. So what are we dealing with? Well, we're given an m by n binary matrix grid. An island is a group of ones representing land connected four directionally, so horizontal and vertical. You may assume that all four edges of the grid are surrounded by water. Right, everything that's outside the grid is water. The area of an island is the number of cells within with a value 1 in the island. Return the maximum area of an island in the grid. If there's no island, return 0. All right. So this is actually, this is a cool problem. I'm just going to switch over to my drawing board and let's have a quick look at this one. So if you've seen the previous video where I looked at, counting the number of islands in a grid, we're going to use a very similar approach where we iterate over with a variable x over all of the columns from 0 to whatever the width is -1. And we're going to iterate with another variable y over all of the rows of the grid. So also from 0 to whatever the height is -1 in the grid. And we're going to start at every xy position. So we're going to have a nested for loop. We're going to start at every xy position if it contains land, and we're going to start to explore the island from that position, count how many cells we visit. So here, this island has only water that surrounds, so the area is 1. So we will, 1 will be our max area when we run into this. Then we continue, blah, 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 blah. Then we run into this island. And now we explore all neighboring land cells with a breadth first search or depth first search approach. And now our max island is 4, because here the size is 4. Then we continue iterating to the end of the row, nothing else. Then second row until we run into a landmass that we have visited before. We're going to use a hash set to remember which cells we've visited before, so we skip over them the next time. And we don't re-explore the island, so we skip over these to the end of the row. And then we run into the next landmass. And we're going to start to explore this island as well. We count the number of cells. It's 4, so we're not going to change our max. Then we continue in the same row. We hit this island, and now what we will see is we will find that we have an area that is 5. So now we need to update our max, and so on and so on and so on. So that's what we're going to do. And it's a very simple approach. We're going to need to have several components. One is that if we have a cell, for example, this one, how do we get the neighbors? So we're going to have a little helper function that returns us the vertical and horizontal neighbors of that particular cell. We're going to have the component with the for loops, right? So we're going to have an x loop. We're going to have a y loop. We are going to check if we visited that cell to skip it, right? Maybe skip. And otherwise, we're going to explore. I wish I could write with my mouse. Well, I can't. We will explore the island, and we'll use our little has neighbor helper function. So that's all there is to it. Let me see. The answer is not 11 because the island must be connected 4 directionally. I guess if you count these 5 cells together with these 6 cells, that would be 11. But this is not a connection, right? Because we don't count diagonal cells as neighboring cells. So when we implement that, we have to be careful that we don't include the neighboring cells in our neighbors list. So that's pretty much it. So I think it's really simple. So the first thing that we want to do, well, what's our time and space complexity? Well, we need to iterate over all of the cells in the grid. So that's width times height. And we need to explore the islands. In the worst case, all of the cells in the grid are part of the same island. And then we need however much space we need to store all of the visited cells. And that's, again, width times height. So the runtime complexity is going to be width times height, or n times m, as it's noted here, time and space. And yeah, the first thing we will do is we will pull out the width and the height from the grid. So that'll be the length of the first row in the grid is the width, and the height is the length, it's the number of rows in the grid. So that's just length of grid. Yeah, so we're gonna need a get neighbors function, and we want to pass in a position that will return us a list of neighbors. And I'm just gonna sketch this out, and we'll implement this in a moment. Then we'll return the neighbors at the end. The other component that we need is our explore island, or we should maybe call it measure island, to know how long the island is. But we're also going to have to update our list of visited nodes. So we should pass that in right away. Visited, like so. Now we need to implement the traversal here, which we will also do. Now for the result, we need to count. What should we return if there's no island? Well, we should return 0. That's the default. And so result contains the max area of any of the islands. And then we just have to have our little for loops. So we're going to iterate over all of the rows in the outer loop in range height, and x in range width. And now we have the position. I'm going to use tuples, and you'll see in a moment why. Actually, I can tell you why, because if we want to check if position in visited, we want to skip over it, right? So we use tuples in Python for that because they're hashable objects, so you can put them into sets. Otherwise, you couldn't. That's why, you know, working with tuples is really useful. Also, when you want to use positions as keys of a hash map, using a tuple is typically the way to go instead of lists or something else. Since list is an unhashable type in Python. Cool. So so that's our first check. Well, the other check is when should we skip over a cell? Well, when it's water, we're not interested. There's no island to explore if there's water. So if grid at position y and x. So first we select the row, then we select the column. If that is equal to 0, now we have to pay attention. In the previous example, I made a small mistake, not knowing whether I should do a string comparison or a number. But here it looks like we're giving a grid of numbers. So we can actually compare this against the value 0. And 0 means that we're dealing with water. If we're dealing with water, we are not interested, and we will just skip over that. Now, if we find a new land of mass that we have not visited before, it means it's exploration time or measuring time. So we'll get the area, and we'll measure the island. We'll start at position, and we're just going to pass it the visited set. So when we measure the island, we can update the visited set and add all the cells that we're visiting to it. So that's pretty much that. And then, okay, we need to be careful to keep track which is the maximum area, right? So we do a result equals max current result and the area. And area could potentially be a larger land area. So that's what we need to do. Next, I will, well, this time I'll implement neighbors as well first. I think I like that because get neighbors is such a, it's a function that has a single purpose, and that's very easy to implement. So for the next x position and the next y position, and I'm going to use this nice zip function here in Python that allows us to iterate over 2 lists in parallel and with 2 variables. So we're going to start at the x position -1. That is our left neighbor of, I'm sorry, I should say this, x, y equals position. So we get our 2 coordinates out of the position tuple, which we created here. So we pull x and y out of the tuple, and now we can do things like this. So what's the left neighbor of a position x and y? Well, it's at x minus 1 and y. Now, what is a neighbor above x and y? Well, x position is the same, but y position is shifted 1 step up. Now, the right neighbor is x plus 1, and y stays the same. And finally, the neighbor below the current position is at x. Oh, sorry, at x, and y, well, y plus 1, right? Now, the next position would be an x and y, and we just have to add that to our neighbors. Whoops. I like to copy these long variable names. I like having longer variable names, and B, it's a pain in the butt to write them out, so just double click and copy them. So that's kind of my workaround to just creating like I don't know, a T list that some people do. I don't know why they do that. That doesn't look nice. But I guess that makes them slightly faster. Neighbors append, next neighbor position. Now, we have to be careful. What if we are at the edge? Well, the up position doesn't exist, and it will yield us, give us an error if we try to check anything. What? Because when we're measuring the island, we need to. What do we need to do? Well, we need to check whether it's land or not. And so this time, let's say, well, we have to filter it. So the first thing is, let's filter out if nx is smaller than 0. Well, it's not in the grid, so we don't care. Or nx is larger or equal to the width. Well, it's also out of bounds. So that position is not a candidate for a neighbor. And next, we do the same thing for the y coordinate. We'll do the same check, except now we're checking y, and we're checking it against the height. And finally, we have to check whether it's water or not. If it's water, we're not interested. So if grid at position ny and x, because remember, we need to select the row first and then the column. If that is equal to 0, well, continue. We're not interested. Continue. Yeah, otherwise, we're very interested. This is land. This is a land that neighbors the current position. So we're adding it. But we're not filtering out by visited yet. So that comes now when we try to explore the island. Right. Let's see. Well, last time I did an iterative approach. Maybe this time I should try a recursive approach, where we're going to use a depth first search instead of a breadth first search. Yeah, we can do that quite easily, actually. So what we can do is, we have to remember what the area is of the island. So how many nodes we are actually visiting. So that will slightly change our approach. If we have visited a node before, let's say we are in this row here, and let's say we've completed this row. Now, when we go into the next row with our little x loop for x in, blah, 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 we run into this cell, but we will skip over it because it already belongs to an previously explored landmass. So that means inside of our land area exploration, we actually don't need to have access to the visited set, right? Because guaranteed, if this is a new area of land that has not been visited yet, it's guaranteed that all connected unit of lands that are also not visited. That's what that means. So if you run into this cell, this is land. We know that there was never a unit of land that was connected to this cell before. Otherwise, we would have skipped over it right here at that position in our code, right? So I'm thinking what we should do is we should, in our code, we should not pass in the visited set. Instead, what we're going to do is we're going to pass in new visited. We should return the new visited nodes, right? Or how should we call this? land or cells. Well, we return the land area, right? Actually, we return the island, right? So we get the island. So I'm just going to call this explore island then. And we just pass in the position from which we start to explore. We get back the entire set, like a set of, so we're going to have our little visited set, and we're going to return that visited set in the end. That's all we're going to do, and we do some magic in between, which I will show you in a second. So yeah, and now, well, the area of the island is pretty simple. It's just the length of the island. That's pretty much it. That's the area. Now we also need to update our visited set after. How does it go? I think it's update in Python. Yeah. For arrays, I think it's expand, and for sets, it's update. So that means that all cells that we visited during the explorations are now added to our global visited set. Right. Cool. And yeah, so now how do we do the recursion? Well, that's a good question. Well, how do we actually do the recursion? Well, we know that we have to explore all the neighbors, right? So why don't we do that? Or next position in get neighbors at the current position. And now all we do is, let me think, all we do is, well, we start our recursive call. So we do explore island, and we will do it from the neighboring position. So, but this will now lead to an infinite loop because we're not taking advantage of our visited set, which we don't have yet. So why don't we just pass in visited, but instead of passing in, well, we're going to call this island, right? So that's the island that we've discovered so far. So this is going to be set, and we're going to do this like this. So every time we call explore from within our two for loops, we're going to start with an empty set. So what we'll do now is we will have a little check. If position in island, we're going to ignore it, right? We're just going to return the island. That's the base case. Otherwise, we need to add our position to the island. Add position, right? And now that we've done that, we can continue to explore the island from all of the different neighbors. And instead of returning island at the end, we're just going to return visited. We're going to return island. And I'm going to simplify this a little bit without changing the logic or the functionality. So if the position is not in the island, we're actually going to add it to the island and continue exploring from that position. Otherwise, we're done. That's the base case. Right. So now we have a recursive implementation. So going back to this example, so the way that would work is, you know, we start exploring here, we go here, we go here, we go here. We don't know in which direction we go next. We might go here, and then we reach the base case where there are no further neighbors that have not been visited, and that are land masses. So we will actually do backtracking, and then we will try the next neighbor of this cell here. And the next neighbor would then be here. And then we run into the base case again. Then we propagate backwards into our recursive call. There are never any more neighbors to explore because we've added all of them. And then we come back to where we started the recursive call. So that's the logic for that. Now that was quite a long explanation, and I wrote code that I haven't written before. So I'm kind of keen to see, you know, if I have any typos or syntax errors. And I actually do. Okay, missing one position argument at island. Okay, so here we go. First error. So I was exploring recursively without letting it know what the island was. And boom, boom shakalaka, the test cases pass. That makes me very happy because it seems to work as intended. So let's submit this. Very nice, and it passes. So yeah, I guess that concludes the max area of island problem, and I think it's easy enough to implement. I really like these kind of problems because it makes it so easy to reason about it. You're able to explore and explain it visually quite nicely. So yeah, that's a really nice one. So I hope you try it yourself.